So now we're coming towards the end of our topic of critical path analysis, and there's one more subtopic that we need to talk about, which is what's called network flow problems. Now this concept is quite different to what we've been doing so far with our activity charts and our network diagrams and these earlier start times, later start times. In this we are talking about the flow through a network. Now you can see I've got a dot point here that says network flow, and it says source, then flow through network, then sink. Now, all of our networks, basically, it's a system of connecting tasks, for example, or this could be connecting roads, anything connecting a system of pipes. There's a few different examples we're going to talk about here, but they all begin somewhere. So this is what we mean by our source. This is where our network starts, and certain things will flow through the network. So you imagine cars going down a system of roads. They are flowing through these roads. And finally, you end up at a sink where it basically ends. Our network ends. Now, you can think of this in terms of a tap, for example. So the source of the water is the tap. You turn it on, the water flows through, and the water hits the sink where it disappears. Now, two analogies I'm going to talk about is roads and pipes to first, before we do anything, get you understanding this idea of flow through a network. Now, we're going to do a little bit of a thought experiment. Say you are traveling down a road, and this road, for example, can fit 100 cars. You're traveling through this road, and say there's 3 lanes. All of a sudden, it condenses. Maybe there's roadworks or something has happened on the road, but your 3 lanes condense into basically 1 lane. Now, say here we can only fit, let's say, 20 cars at a time. Now you're driving through here, so the cars are going in this direction. This is our source, we'll call it. This is where our road starts. And we get to what we call a bottleneck. Now, you may have heard this terminology on the roads. Basically, you can see this entire thing looks like a bit of a bottle. You have the bit down the bottom here, this section, and then like a bottle happens, think of a bottle of wine, it goes in, and you have this neck portion here. Now, what happens here is now our flow of cars drastically decreases. So we can no longer fit as many cars in this smaller road as we could in the larger road beforehand, once our lanes, for example, merged together. Now, this is going to be our sink. This is basically, we're going to say where our network ends. And we are considering basically what the maximum flow of cars is through this network at any given point in time. Now, if we were to say cut off from here and just looked at the left side, we would say, sure, our maximum flow is 100 cars. But the whole network, these 2 sections here, our maximum flow throughout the entire network is limited by this bottleneck. Because only 20 cars can pass through here, then we say the maximum flow through the network is 20 cars. At any given time, this is basically our limiting factor. It's saying that even though we have these 100 cars earlier, throughout the entire system, we're limited by this bottleneck that will only allow 20 cars to pass through. Now let's extend this example a little bit further. Imagine we exit this little bottleneck and all of a sudden we go to a bigger road where we can fit, say, 150 cars. Say we gain an extra lane or something. Say you're coming out of a tunnel and there's more lanes all of a sudden. So your cars flow through here. We have a bit of a bottleneck, so we get a lot of kind of bumper to bumper traffic. You can see a lot of cars kind of packed in here. They're basically taking a long time to go. Why? Because there's 100 cars coming in into a condensed space where you can only fit 20 cars. So all these cars are packed in, they're beeping, there's bumper to bumper traffic, and all of a sudden they exit and flow out through to here. Now you may be thinking, well, I'm going to look at the biggest number. Now our maximum flow through here is 150 cars. This idea, although it may sound counterintuitive, is actually incorrect, because if we consider our sink here, even as we exit this little bottleneck and we have more space, we are still limited by the flow through the smallest system of the network. Only 20 cars can pass. So even as they exit and go into this third portion, they can drive faster, but it's still only letting out 20 cars because we're still filing out from this section in here. The cars are kind of exiting through here, but the rate at which they pass through the network has slowed, and it's slowed to this smallest system here. Now, may sound a little bit weird and counterintuitive. We're going to look at one more example, then define one little key idea that's going to send us through to the next video. Now, the second example I'm talking about is pipes. So you imagine water flowing through a system of pipes, okay? Now, let's say we have a pipe over here, and the amount of water that passes through it is 58 liters per minute. So we go through here, this pipe kind of ends, and we have a smaller pipe that continues through to here. Now through this pipe, we can only allow 25 liters per minute. As the water flows through here, the exact same idea is going to happen. We have a really fast rate earlier, right? A lot of water's going in, but you're going to get a lot of bottling up in this section here. All of our water that's passing through suddenly significantly decreases. It's all banked up here, and our flow is reduced as we pass through that second pipe. So once again, we're limited by our smallest pipe, our smallest individual pipe here. Now, if something happened where, for example, we had, let's just change this picture up a little bit. We're going to extend this forward a little bit, and we go through, say, a bigger pipe. That can get maybe 70 liters per minute. Then we still have this same bottleneck thing as with our traffic example. The water is packed in this section here because not a lot of water can pass through here. We have drastically lowered our flow rate of water to 25 liters per minute. So even when we get out to here, the water is still flowing. It's limited by our smallest pipe. So even as it exits, even though there's more space in this pipe, the water's still flowing out at a rate of 25 liters per minute because this middle pipe is like our limiting step. Because the rate's so much lower, it affects the flow through the entire network. Now, this is summarized in this key idea down the bottom, which is saying, this more talks about this last example, but if pipes of different capacities, what we mean by that is different sizes, how much water they can hold, are connected one after the other, so this is a system, it's like a network, they're all connected together, the maximum flow through the pipes is equal to the maximum capacity of the individual smallest pipe. This is our most important bit here. It's limited by the maximum capacity of the individual smallest pipe. Here it was 28 liters per minute. That was our smallest pipe. Here, our smallest road accommodated 20 cars. So if we look at this as an entire system here, so our network in this first example is 3 roads. Here our network is 3 pipes in total. Throughout the entire system, the rate is limited. The maximum flow through the pipes is equal to the maximum capacity of the smallest pipe. This is a key idea, this idea of being limited by the smallest pipe or the thing with the smallest weight on a network. That will limit flow through our entire network system. We'll look at some examples in the next video where we can clarify this bit a little bit further, but this is just to give you an introduction into how we can describe flow throughout a network. Thanks so much for watching, and I'll see you next time.